Hi all, we are going to finish up with momentum with 2D collisions. This is 4.3. Please read Coletta Chapter 8 if you haven't done so. This is going to be related to Homework 10 if you're in Physics 111, Homework 7 if you're in Physics 121, and also Labs 10 and 11 in the lab book. So here is, so now we're going to go ahead and begin momentum in 2 dimensions, right? And so this entire time we've been talking about, well, for the last 2 activities, we've been talking about conservation of momentum. And this particular problem is a problem when how momentum is not conserved, right? And we talked about within a system, the momentum is conserved, right? But if there's any outside forces that come into the system, it's going to be changing that momentum in the system and adding to it or subtracting from it if it's leaving the system, right? So, and the system in this case just contains the ball. So I'm going to mark up this document, and I want to illustrate what is being demonstrated here by this problem. Okay? So here we have a ball, right? And this ball is going to be coming in right here. And it's coming in with an initial momentum. Now when it hits this wall, okay, the wall is going to go ahead and give this ball a force. And it's going to push it directly outwards, right? If it's coming up and to the left, right, it's going to continue moving up, right? Correct? So it's going to continue, so it's got an initial momentum in the y direction upwards, right? And that is going to continue moving upwards. If this angle right here, if this angle is equal to this angle, then this momentum is equal to this momentum. And here's what I mean by this. The initial momentum in the y direction, let's just assume that they're equal, right? Well, this momentum right here in the y direction is going to be equal to the initial momentum sine of theta, correct? And that's going to be equal to the final momentum sine of theta. Well, those thetas cancel out, and so just what that means is essentially is that, well, this entire system is canceling out. So what we're saying is basically the initial momentum in the y direction and the final momentum in the y direction are equal. Okay? So what you could say is this: if you're given 2 blocks of initial momentum in the y direction, that's going to be equal to 2 blocks initial momentum in the y direction. And that's what they're kind of saying here, right? The total change in momentum in the y direction is going to be 0, right? But let's look at this, right? In this case, so this force isn't going to be changing its velocity or momentum in the y direction. All it's doing is it's changing the x direction momentum vectors, right? When it's coming in, its x direction momentum vectors is pointed to the left. After the impact, now that final momentum vector in the x direction is going to be positive. Initially, it was negative, right? Right? And you cannot say this. You cannot say the initial momentum vector, which is negative, is equal to the final momentum in the x direction, because that is positive. So they're not equal, right? Which means this is an outside force, okay? So in the x direction, let's say it had 2 blocks initial momentum in the x direction, which is going to be negative, okay? And then afterwards, it's now got a momentum vector, the same size momentum vector as well, right? In the positive x direction, that means this force vector right here, and I'm going to use a different color for that force vector. I don't like that. In fact, I'm going to get rid of this. I'm going to call it, oops, come on, just trying to erase. That force vector, okay, that force vector is an outside force to the system, and that force vector is going to take a -2 and turn it into a +2. That means it's adding 4 blocks. 1, 2, 3, 4. Did I add 5 blocks there? Let me see. That's 1, 2, 3, 4 blocks. There we go. Now I could add. So that means in the x direction, there has to be an impulse to the right. In other words, you're going to have a positive force vector in positive x direction that is changing its initial velocity vector, initial momentum from negative to positive, right? And that's kind of what we're seeing here when they work this out. So in this case, the momentum really isn't conserved because when the ball was coming in, our system was just the ball. It was the wall, this wall, which was adding an outside force to our ball system to change its momentum in the x direction. Okay? So if you're ever given a problem where a ball is bouncing off a wall, just know that the wall is going to be changing the ball's incoming momentum in one direction or another, in this case in the x direction, such that it's adding an outside force to the x direction vector, but the y direction momentum vectors is staying constant, is actually conserved. So it's interesting. Only the x direction momentum isn't conserved. The y direction momentum is conserved in this case, and that's because this ball system, it's the momentum in the y direction wasn't being altered. It was the momentum in the x direction which was being altered. Okay? But when we do collisions, so this is just an impulse problem, but when we're doing two-dimensional elastic and inelastic collisions, the momentum is going to be conserved. Okay? And we had learned also that with elastic collisions, kinetic energy is being conserved. However, with inelastic collisions, kinetic energy was not conserved. Well, how do you do a momentum problem, a two-dimensional elastic collision problem? Well, here we have a ball A. So I'm going to note that right here. This is momentum A, and this is momentum B. This is momentum A, momentum B, momentum A, momentum B, A, momentum B. Okay, so you have ball A coming in, and it's going to hit ball B. And so this guy's momentum is 4 times 0.5, so this momentum vector is going to be to the right at 2 kilograms meters per second. And that's the initial momentum vector, right? After they hit now, that initial x direction momentum, and let's do this. I'm going to give it 4 blocks. 1 block for each momentum, okay? So it's got 4 blocks initial momentum. Initially, this guy has 0, right? So this guy's initial momentum, block B, is 0. Well, now, let's say ball A is moving off at 60 degrees, and ball B is moving off at 30 degrees, right? And you're asked to find out what ball B's velocity is after this impact, okay? Well, this ball A is going to have two momentums. It's going to have an x direction momentum, okay, and that's the momentum in the x direction after the impact. So there's a lot of subscripting in here. There's ball A's momentum in the x direction final, and it's going to also have momentum in the x direction, in the y direction final. Ball B is going to have also its own momentum in the x direction final, and it's going to have a momentum in the y direction final, but this guy is going to be negative. This guy is going to be positive, right? So here you go. Right? Well, that means if it's got 4 blocks in the x direction here, okay, in the y direction, it actually had no momentum in the y direction and no momentum in the x direction. So both objects had no momentum initially in the y direction. So that means in the y direction here, one of these blocks, the block A, is going to have a momentum up, and block B is going to have a momentum that is negative. And what that means also in the x direction, both objects are going to have a momentum in the x direction. And since they're going off at unequal angles, I'm going to assume that one of these objects is going to have more momentum than the other. Not sure. No, they're going to have, I don't know if they're going to have equal momentums. So I'm going to just make it unequal for now. Okay? So we're making our best guesses at stuff. Okay? And we'll see how it works out. Okay? So what we're going to do is we're going to sum the initial momentum in the x direction and set that equal to the initial momentum, to the final momentum in the x direction. Well, in the x direction, it had a momentum initially of 2 kilograms meters per second due to ball A. Ball B had 0 kilograms meters per second. And that's equal to, in the x direction, ball A has, this is going to be half a kilogram times 2. So let me make some notes over here. So P initial A in the x direction is going to be 2 kilograms meters per second. In the final, it's going to be PA X final is going to be, what is this? This is going to be, it's a half a kilogram, so 0.5 kilograms times 2 meters per second cosine of 60 degrees. 2 meters per second cosine of 60 degrees. Okay? So that is what? 1 times cosine of 60 degrees. So 60 degrees, trigonometry, cosine is going to be 50%. So this is going to be 0.5 kilogram meters per second. Okay? So in the x direction, it's going to be moving 0.5 kilogram meters per second. right? Well, if this is 2 over here, and this is 0, so this side has to be 2. So this is going to be 2 kilogram meters per second. This has got to be equal to 0.5 kilogram meters per second plus, so that's going to be plus the y direction, the x direction of P, B, X, F has to be the rest of this 2, which is going to be 1.5 kilograms meters per second. Okay? So that means it's got to be 1.5 kilograms meters per second. Right? If I bring this onto the other side, so hopefully, yep, it works out. So that means PBF is equal to 1.5 kilograms meters per second. And that's equal to mass times mass of B times its final velocity, PB X final, okay, which is equal to 1.5, which is, and then the mass is 0.3 kilograms, right? And VBXF is going to be its velocity, VB, and that's that's velocity V final, and I said the angle was cosine, and that'll be 30 degrees, right? So what we could do is, if you got 1.5 kilograms meters per second, divide that by 0.3 kilograms and cosine of 30 degrees, and now we have the velocity of VB final. Okay? So 1.5 divided by 0.3 times 30 trigonometry cosine in parentheses equals 0. Okay, let me just make sure that's right. I think I might have made a mistake. 1.5 kilogram meters per second divided by 0.3, and divide that by 30 degrees cosine equals 5.77. So this final velocity is going to be 5.77 meters per second. Okay? Which means it's going to have a lot more momentum in the x direction. Notice that in the y direction, so notice in the y direction, there might be the same thing. I'm not sure. We could calculate the momentum in the y direction after the collision. PAYF is going to be equal to 0.5 kilograms, and that's going to be 2 meters per second, cosine of 30 degrees. Okay, well, what is that equal to? .5 times 2, 1, great, I don't know why I just did that, times 30 degrees, and I said that was going to be sine. That should be sine. Equals, which is 0.5. And that should be sine. Erase that. In the y direction, it'll be sine. That's equal to 0.5 kilograms meters per second. So what does that say? Well, that if this is 0.5 kilogram meters per second, then the PBY final has to also be 0. If this is going to be positive 0.5 kilogram meters per second. Well, that means this has to also be 0.5 kilograms meters per second, but negative. So these two are going to be equal. And what that means is this is going to be positive 0.5 kilograms meters per second minus 0.5 kilograms meters per second. And that is a velocity in the wide. That's the overall velocity traveling for object B final. So this is kind of how you kind of reason through these problems. Okay, and these momentum bar charts are really, really powerful in solving these problems. Okay, so that's an example of a 2D elastic collision problem from off-axis. So now let's move on to a 2D, and that should be inelastic collision problem. Had to change that. Thank you. So this is going to be an example of a 2D inelastic collision problem for initial momentum off axis. So here we're going to have a 2,000 kilogram Cadillac and a 1,000 kilogram Volkswagen are going to hit. Right? They're going to hit each other from off axis. Okay, and so they talk about the accident scene, and the officer measures the angle at which they were traveling off axis. Well, the angle that they were traveling at after the impact was at 35 degrees northeast, which means up and to the right. Okay, and the Cadillac driver keeps a close eye on the speedometer and reports that he was traveling at 3 meters per second when the accident occurred. And so we want to know. How fast the Volkswagen was going, in order to try to figure out who's at fault. Okay? So I'm going to get ready to mark this up. So we know that the momentum during an inelastic collision is conserved. It's always conserved, right? So let's go ahead and move to the problem. So in here they go ahead and graph this. They say the Volkswagen was traveling to the right at some unknown velocity. And that's at and it weighs 1,000 kilograms. In the y direction, the Cadillac was traveling upwards at 3 meters per second, and it weighs 2,000 kilograms. Okay, so let's go ahead and start marking up this document. Okay, so here we go. I'm going to take a look at the initial picture, and let's just make some guesses as to the momentums. Okay. Well, the Volkswagen is going to have a positive x direction, and this is the Volkswagen, and this is the Cadillac, okay? And this is the Volkswagen, this is the Cadillac, and this is both of them, the Volkswagen plus the Cadillac, because they're combined. They've impacted after the accident. And now they're a combined mass moving at 35 degrees at the final velocity. So here we go. The Volkswagen has only a momentum in the x direction before the accident. Okay? While the Cadillac does not. And I just put 3 blocks there just because. Okay? In the y direction, the Volkswagen has no momentum, and I'm thinking, if this is 35 degrees, that it's going to have maybe 2 blocks. I'm thinking 35 degrees is a pretty steep angle, so most of its velocity is going to be caught up in the x direction and not the y direction. So I'm thinking just 2 blocks in the y direction of its initial momentum. Right? Because after the impact, if momentum's conserved in both directions, this is going to be 3 blocks here as well. And this is going to be 2 blocks as well. Okay. So I'm just marking up the document, and I'm kind of making some guesses as to its momentum. So the momentum in the y direction of this guy is going to be 2,000 times 30. So it's going to be 6,000 kilograms meters per second. After the impact, the momentum upwards is going to be the mass of this guy. It's going to be the mass of this. Okay. It's going to be the mass of and I'm looking to see if there's a final velocity. No, there's not. So it's going to be the combined masses, right? Which is going to be, 2,000 plus 3,000 kilograms times the final velocity sine of 35 degrees upwards. It's also going to have a momentum to the right of, again, 3,000 kilograms combined, final velocity cosine of 35 degrees to the right. And so this represents the momentum in the y direction right here, and this represents the momentum in the x direction right here. Should be careful, those looks like those two lines join, in the x direction right here. Okay, and we know, again, we know this is the initial, so this is going to be 6,000 kilograms meters per second, and our unknown, so we have some unknowns. We don't know the final velocity after the impact, and we also don't know the initial velocity of the Volkswagen before the impact. Okay, but we know everything else. Okay, so here's what they did, is they took the x direction and y direction momentums, okay, and then they're going to solve for one and plug it into the other one, okay? What they're saying right here is they're saying the initial velocity of the Cadillac here in the beginning is 0, right? So this initial velocity of the Cadillac in the beginning is 0. That's going to be equal to, plus the initial velocity of the Volkswagen in the x direction, which is not 0. So they're saying this is going to be equal the initial velocity in x direction for the Volkswagen. Okay, so they're saying this, and they're also saying this, that the final momentum in the y direction is equal to the initial momentum of the Cadillac in the y direction. Okay, so then what they're going to do is they want to get what the final momentum is after the impact, right? So they're going to be using that y direction momentum, and I'll go back to that. Okay, so we know the momentum of the Cadillac, so the mass of the Cadillac is 2,000 kilograms, and it's, 3 meters per second, right? And that's equal to the combined masses of the guys, the mass of the Cadillac, right here, plus the mass of the Volkswagen, times their final velocity combined, sine of 35 degrees, right? So what they're doing is they're going to go ahead and solve for the velocity of that stuff combined. So this is going to be 6,000 kilograms meters per second, and they're going to divide that by the 3,000 combined mass kilograms sine of 35 degrees, right? And so that's what they're doing right here. And they're getting that final velocity to be 3.49 meters per second. Well, now what they're going to do is they're going to plug that into the x direction equation, which is right here. So now we know what this is, which is 3.49 kilograms, nope, just meters per second, because we found it from here. They plug it into here, and now they're going to solve for the initial velocity of the Volkswagen, right? And that initial velocity of the Volkswagen is going to be the combined masses, right? So I'm going to just copy this equation down here. It's going to be the combined masses, 3,000 kilograms, times that final velocity after the impact, which is 3.49 meters per second, times cosine of 35 degrees, divided by the mass of the Volkswagen, which is 1,000 kilograms, and that's going to be equal to its initial velocity, the initial velocity of the Volkswagen, right? And that's how they got it to be 8.62 meters per second in the x direction, okay? So again, you with these two-dimensional problems, what you're going to have to do is you're going to have to storyboard the problem, define your variables and vectors using subscripts, make momentum bar charts both in the x direction and y direction, and then start solving them, because eventually you're going to have to merge those two equations together, the x direction momentum and y direction equations. Okay? Anyways, that's how you do two-dimensional problems. I hope you had a good time. Please do the lab, and please do the worksheets, and also your Sapling homework. Thank you.